In this video, we're going to look at testing for significance of regression. But to get to that, first we need to look at the model assumptions. Our multiple regression model is y equal to mean of y given x plus an error term, where mean of y is this part. Given this, we have four assumptions very similar to the simple regression case in the previous chapter about the regression error. So the first assumption is the error term is a random variable with the expected value equal to 0. If this is so, then the expected value of y will be that part. That's our mean of y. The second assumption is that the variance of the error term, sigma squared, is the same for all possible values of all the different x's. So this is the constant variance assumption. Again, we made the same assumption in simple regression also. The third assumption is that the values of E are independent of all the x values that we may use. And the fourth assumption is normal probability distribution for the error term. Now all these four assumptions can be looked at in this graph where we have x sub 1 and x sub 2 as the two independent variables and the value of y, and this three-dimensional plane represents the mean of y, beta sub 0 plus beta sub 1, x sub 1 plus beta sub 2, x sub 2. So this plane, the three-dimensional plane, is the mean plus an error term, either positive or negative, that will determine the actual value of y. Given these assumptions, then we can test for significance of regression, where if all the beta coefficients are 0, so that means regression is not significant. And if one or more of the parameters is different from 0, then the regression is significant. Now the test for this hypothesis is F test, and when from the ANOVA table we get the MSR, mean squared due to regression, which is SSR over its degrees of freedom P. Then we have MSE also from the ANOVA table, SSE divided by its degrees of freedom. And then we divide MSR by MSE to get the F statistic, and from F statistic then we can compute the p-value using the f.dis.rt function. Now of course ANOVA table also gives you significance of f, and that is our p-value based on which we can make a conclusion. If we reject the null hypothesis, and that is if we conclude that the regression is significant, then we have to do individual significance test for each and every parameter beta sub I. Now this is done with the t-test. ANOVA table gives you the t statistic value, which is b sub 1 over s sub b sub 1, and we can then determine the p-value using the t.dis.2t function, or we can use the significance value from the ANOVA table, and you can perform the test in that fashion also. Before we go to the Excel file, we have one more concept to talk about, and that is multicollinearity. And that is when we have multiple x columns and multiple x values, if the x's are correlated among themselves. Now in a regression analysis, we want the x's to be correlated with the dependent variable y. If x and y are correlated, then that adds to the predictive value of x in predicting y. So you want each of the x values to be highly correlated with y. But if the x's are correlated among themselves, and that's not good, that is bad kind of correlation, because it will compete to explain the same variation in y, and that will result in unforeseen or unexpected parameter values and so on. So we don't want the x's to be correlated among themselves. So there is good correlation, there is correlation between X and Y, and there is bad correlation, which is correlation between X's themselves. And that bad correlation is called multicollinearity. And if the correlation is above, say, 0.6 or 0.7, either on the positive side or on the negative side, then you would consider the correlation to be really high, in which case we have to drop one of the two X variables out of the model. Now in the next video we'll look at the Excel example.